Good afternoon, everybody. My name is Andrew Collins. Today I'm going to be going over my persuasive speech in accepting the heat depth universe. Andrew Collins, my audience, point to the audience. 1, 2, 3, 4. And then one cameraman makes 5. So without further ado, let's jump right into it. What is the heat depth universe? The fate of the universe is sealed and will ultimately reach the same temperature. So what does that mean? It means that the entropy within an isolated system, which we'll go over in a second, makes a uniform temperature. You can point it to the audience and kind of do like a transitional thing. It's going to make a uniform temperature within an isolated system. The reason being is because within an isolated system, mass and energy may not pass through, thus leaving the energy that's inside an isolated system to be contained inside the isolated system, meaning with two objects of two different temperatures that are close together, one will draw from the other. The cold reservoir will pull from the heat. Now we're about to break that down and go into it so you guys can understand. So, how though? Well, to understand how, we need to first understand what entropy is and how the heat transfers between different systems. First, we're going to go over the types of systems. We have an open system, which allows energy and mass to pass through the container or reservoir, and will be referred to as both during the speech. A closed, which will allow energy or heat to pass through a container, but will not allow mass to pass through the container. And then we have isolated. With an isolated system, energy or mass may not pass through the container and or reservoir. So what does that mean? As I explained before, the energy inside of this, the heat inside of this, is trapped inside of this. So within an isolated system, you can have multiple open and closed systems within it, but they will affect each other's heat and how they transfer heat. So, here we go. As you see, an open system, energy and mass can freely pass. Closed, only energy may pass. In an isolated system, neither can pass. The universe is an isolated system. I know a lot of you are thinking, well, the universe is endless, right? Well, that same concept can apply to an isolated system and its energy within it. It's a hard thing to grasp. If you classify the universe as open or closed, what are you doing? You're limiting the space of the universe, which can't be done. So, you may hear heat, temperature, energy. They all mean the same thing in this speech. They're all considered, I just said that. They're all considered the same thing. So what is entropy? Entropy is the unavailability of a system's thermal energy for conversion into mechanical work. So what does that mean? It means that energy, let's say in a combustion engine, you use heat to perform work. Work is considered mechanical work based off of heat, also known as joules. Work is required to produce order out of disorder. So energy must be used to produce a highly ordered state. So entropy in itself is kind of a way to measure chaos, hypothetically speaking. So an example of an entropy system would be a campfire, because a campfire, same with making popcorn, salt or sugar dissolving, are all irreversible processes. Now, there are reversible processes that can include entropy. For, like, example, deck of cards, right? If I buy a deck of cards, it's perfectly suited from 2 to ace, or joker, or whatever's in it. If I throw that deck of cards, pick them up in any order, have I increased the entropy of that deck? By causing disorder? Yeah. Alright, so moving on. So what the heck does all this have to do with the universe ending? The question we've all been looking for. Well, to mathematically prove in theory the heat depth of the universe is that a uniform temperature must be reached in an isolated system at some point in time, like all isolated systems, thus causing all molecular levels of heat distribution to be the same amongst all molecules in the universe. Pretty self-explanatory, right? All these systems, open and closed within the isolated system itself, over time pass their energy between each other, because in an open and closed system, energy may pass, mass may not. But mass is not a factor when talking about inside an isolated system, which is the universe. Technically, everything is inside an isolated system. So, I forgot to go over the equations for converting the heat and calculating entropy. So, delta S is the change in entropy. Q rev is the reverse of heat, and T, or sometimes referred to as K, is Kelvin temperature. So this means, this equation here, delta S, meaning system equals Q rev over T, which is another word for saying that the reverse of heat in over the temperature is the same thing, or is true to the factor of delta S, or entropy, change in entropy. As heat enters a system, like open and closed, its entropy increases. As heat leaves, entropy decreases. But what about isolated systems? Because that's what we're all here for, right? Well, in an isolated system, there can be different systems inside, and we use this to calculate entropy. Example equation is two closed open systems within an isolated system here. So here we have delta S, isolated greater than open heat. Very confusing, I know. I'm going to explain it here with this circle. But that is equal to reservoir or container hot over temperature hot. So what does that mean? Heat and work, object temperature. So we have negative joules inside of an open container that is 350 Kelvin. So negative joules, as I explained before, is joule is expressed as negative. Is expressed as negative work because heat is leaving. So even though it's a hot object, heat is leaving because it's too hot for the environment for the isolated container. Thus evening itself out to an equilibrium with temperature. But because heat is high and the work is negative, we can now calculate and quantify how delta S isolated is less than object cold at 100 joules and 200 Kelvin. So with these placed beside each other, one is losing heat at negative 100 joules at 350 Kelvin. Now the cold container is gaining work at 100 joules and 200 Kelvin. Because they're beside each other, the temperatures don't really per se matter, but the work being involved, the work that leaves the hot container is being forced into the open container. But you can see there's a huge difference within the temperatures. So eventually, because this is negative 100, this is 100, they will reach an equilibrium in heat, or object temperature. And that will be what is referred to as the equilibrium. We can now, this means even though one object is colder, the entropy is greater, chaos, disorder, than of the hot reservoir object. Meaning this equation here, delta S cold is greater than object, delta S hot is less than object, O equaling the object. So now that we know how to do that, finally the end man, because we know how to do all this. The universe as an isolated system is described as delta SU, meaning universe, is greater than 0. Why? Because this is not a reversible process. Like mentioned before, campfires, popcorn, salt and sugar dissolving is not a reversible process. Because when you burn a campfire, it turns to ash. You can't put that back together. Making popcorn, hot. You can't make that a kernel again. And then salt and sugar dissolving. You can't recompound them. So the cold and hot objects will be described as H equals C, leaving one constant temperature, where energy is no longer produced or transferable between objects, causing the endlessly expanding universe itself to be classified as a temperature equilibrium object due to the limited amount of energy in the universe. This energy is not infinite. We create it. It takes up space. But because we're in an isolated system, this energy is going to eventually take over all the mass, because in an isolated system, what cannot enter? Mass cannot be created. It is set. What else cannot enter? Energy cannot enter, but it can be created within. So me moving this, me doing this, me talking is all creating more energy within the isolated system. But energy may not freely pass. So what if the process is reversible? According to the third law of thermodynamics, delta S universe is equal to 0 is not achievable because the temperature is not equal to 0. Pointed out here, by applying, that's supposed to be a K, by applying Kelvin 0 or 0 Kelvin to temperature object, you would need an infinite number of 0 Kelvins. Without infinite number of 0 Kelvins, it would apply to temperature Fahrenheit object as temperature Fahrenheit half, 1/8, 1/4, 1/8, and repeating, thus making it an impossible Fahrenheit temperature to reach. But quick maths for you guys too, fun facts. If mathematically broken down, this equilibrium will occur in 10 years to the 100th power. So we're supposed to change that. So that means in 100, comma 00, and then 92 more zeros is when the universe will reach this equilibrium of heat and temperature. I cited for this. I used YouTube. I used thermodynamics.com, and I used Fundamentals of Thermodynamics, book version 2012, written by some cool dude. So with all that information on accepting the heat death of the universe, did I persuade any of you into accepting this as your inevitable fate, regardless what stature of molecule you are in that year, which is also called a Google, by the way. Wonderful. So we can all start praising the sun and worshiping the heat.
I'm a believer.
He's a believer.
We're all gonna die.
All that